Hello, my name is Tyler Ventima, and this is my first lab report on the amount of excess charge on an ordinary object. This experiment asked us to look at Scotch tape in particular to generalize to everyday objects, to see if we could create charge on them, and then subsequently see how much excess charge we have created. Going into the experiment, we were given that the range of excess charge on a tape should be anywhere from the elementary charge of a proton to 1 e to the 5 coulombs. So in the end, we have to make sure that our answer matches up to these values. To get to this point, though, we will have to go through multiple physics principles and equations in order to calculate the electric force, electric field, and excess charge of the charge tapes that we've created. On this screen, I've listed both my initial and final values. Initial values include tape length and tape mass that I measure at the beginning of the experiment, and final values include almost everything I've found throughout my experiment, going through the steps. Our found excess charge was proven to be between the desired range, and this was proven both by my hand calculation and my Python calculation. The code can be accessed through the link on the right. Though, to fully understand the results of this experiment, I'm going to walk you through the basic steps that I used to calculate all these numbers. To begin, it was important to determine the charges on both of the tapes after ripping them off the base tape. This was done by comparing the tapes to multiple objects. When compared to neutral objects, the tapes were attracted, which tells us that the tapes had some sort of charge or another. When compared to a negatively charged pen, the tape was also attracted, which tells us the tape is either neutral or a positive charge. And then, when compared to each other, both tapes repelled each other, telling us that they have the same sign of charge. We were able to conclude with all our newfound information that both of the tapes were positively charged in this situation. Now that we know both tapes are positively charged, we can choose to observe the repelling distance between both of them. We did this by placing one piece of tape on top of two books and approaching it with another positively charged piece of tape. Now, we didn't get the tapes to actually float above each other in our experiment for reasons I'll address later on in the video, but in the theoretical scenario that we assume would happen, the net force at the top of flotation would have to be 0, because the piece of tape is not accelerating into the sky. For this to be true, the electrical force of A at B would have to be equal to the gravitational force at B. Using this knowledge and assuming that the tapes are observable as point charges at their center, we can calculate gravitational force and set the electrical force equal to the negative of that number. This has to be true for the net force at B to truly be equal to 0. Now that we know our electrical force at point B, we can use the electrical force equation in the top right of this screen to derive an equation for Q. We normally do this if we assume that both the tape's charges are equal in magnitude, so that we can change Q1 and Q2 into Q squared. This derived equation for Q looks something like square root of F times R mag to the power of 2 divided by 9e to the 9. This yields a total charge that falls within our range, once again proving that this experiment was a success. Now to get into the follow-up questions we were asked after the experiment. So the first question proposed to us here is, what if electrons in our problem had a positive charge and protons had negative charges? What would change about our observations that we made with the tapes and other charged objects? So first I would like to begin by looking at the system where both the tapes had a positive charge. In this situation, we were able to observe that the electric force at B by A was in the positive y direction, which you can assume because you would assume the two protons would repel each other in the end. Now, if we take into consideration the question we're being asked and make both of these negative, we can observe almost the same thing. At B, the electric force by A is still in the net positive y direction because both the electrons will continue to repel each other, so nothing really changes in this situation. Also, if you look at all the times that the positive tapes were attracted to neutral objects, none of that would change either, because neutral charged particles can attract protons and electrons. So the second question asked us is, why is it important to handle the charged tapes as little as possible? What happens when the charged tapes come into contact with our hands or other neutrally charged objects? Well, the answer to this is simple. The neutrally charged objects transfer electrons to the positively charged tape, balancing out the charge of the tape and really making it lose its charge altogether. And as you can see here, I have it written, this may seem incorrect as your hand usually won't have a positive charge, but electrons in the environment quickly replace these transfer electrons, keeping our hand a neutral charge. This really can be used to explain why we weren't able to get our tape to float when we conducted the experiment, because the books that we were placing the tape on were neutrally charged, and the hands that we were using to transfer it to the books were neutrally charged. So multiple electrons could have been transferred in this situation.